Okay, in this next module, we're going to continue in Chapter 25 with Section 25.3. And here we're going to discuss something called the resistivity. The resistivity is the inherent resistance for a given substance and not just for a given object. Now, what do we mean by that? Well, if I give you some resistor, I have to tell you, for example, this pen that I'm holding, this green pen, would have a certain resistance, and it might be 27 ohms. But if I look at the top of this pen made out of the same substance, I would have to tell you again that it's only 12 ohms. And so for each part, or each different object, we have a different resistance value. I'm going to erase that now. We could ask the question, when we have a resistance, is there a way, if we know the substance, to figure out what the resistance of that is if we know its geometrical properties? In other words, if we know it has a certain length, and we know it has a certain area, and this could be a cylinder or a little square area. If it has an area at the end and a length L, is this enough to determine, if it has it made out of a certain kind of substance, what its resistance is going to be? And the answer is yes. And that's given by a formula that says that the resistance of an object is equal to the resistivity, and that's the resistivity is rho, times the length, I used a small l, so I'll use a small l here, divided by the area. And rho is here defined for a given material. Some examples are, here's the resistivity of silver, of copper, aluminum, of iron, wood, glass, and if you look at these, this is small. Silver has a very small resistance. So does copper, 10 to the minus 8. Even aluminum. And as you may be aware, all of these can be used for wires. Iron is a little bit higher. It's about almost 10 times or 8 times as much as silver. Carbon, that's kind of close there, but the carbon is 10 to the minus 5, not 10 to the minus 8, 1,000 times greater. Wood is 10 to the 10th. That's a power of 10 plus another 8, 18 powers greater for wood, and glass can be up to 10 to the 14th. Things that admit current to flow easily are called conductors. Things that impede current, like carbon, wood, and glass, are called insulators. And so now we can say, if we know this, can we compute the resistance? And of course, this is a formula you need to remember. And this is a length in meters and an area in square meters and a resistance in ohms. So this is ohms, that's the Greek letter for the last letter of the alphabet, omega, is equal to rho times the length in meters divided by area in square meters. So rho is going to have units of, since this is meters, I should write it as meter squared. If I take this meter and cancel one of these meters here, then I'm left with 1 meter, and rho can be seen to be a meter times an ohm. And those are the units that we have here, which are the SI units for that. So if I give you the length and I give you the area, then we can compute what this would be. For example, if I had 1/10 of a square meter, and it was 100 meters long, and it was made out of, let's say, copper, then we'd find the resistance for this object would be, let's round this off, 1.72. I'll just round it off to 2e to the minus 8. And I'm going to make it a length of 40, or I've forgotten what I said now, a length of about, let's say, 100 meters long, and 2 meters in cross-sectional area. Of course, that's a huge block of copper. we'll make it smaller than that. We'll make it 2/10 of a meter. Not that it'd make much difference here in area. That would be about 1/5 of a square meter. So we could compute what this would be, and as I take this 2, it will cancel this 2. I've got a 1/10 down here, so it becomes another factor of 10 in the numerator, so that's 1,000. That would be 10 to the minus 8 times 10 to the third, 2 powers here and 1 power from here, and the 2's cancel. So that would give me 10 to the 5th ohms. 10 to the minus 5th ohms. So it's only 10,000th of an ohm for that huge big block of substance. So this is the way we can use resistivity to figure out the resistance of substances. This allows us to catalog different materials and then compute what the resistance is going to be. However, it turns out, as you see from this formula right here, that resistance depends upon temperature. And as we change the temperature, the resistance is going to change. So our formula is the rho is going to be equal to rho at a fixed temperature times 1 plus alpha times T minus T naught, the reference temperature. This reference temperature is usually given as something like 20 degrees Celsius, more like a room temperature. But this formula right here, you also need to know. And if, for example, we knew the factor alpha, which would be given to you on the test, then, and we gave you the temperature, then you could figure out what the new resistivity was. So we would take something like, again, copper, which would be 2 e to the minus 8, and I'm rounding off there, around that 1.7, I just rounded it off to 2, times 1 plus alpha onto, let's say it's at 40 degrees, it'd be 40, let's say 30 degrees, 30 minus 20 degrees, and that would give us 10 degrees times alpha. And I don't know what alpha is for that particular substance, but that would be given to you on the test. Let's say alpha, for example, for silver might be 0.0001. Then I would have a 10 that would multiply this, and I would have, this would be, would give me a result of 2e to the minus 8 multiplied by, I've chosen an alpha that's pretty large there. It would be times 1 plus 10 times this would be 0.001. So that's a 1.001 times this, and that would give us our resistivity. Using that resistivity, you can plug it in this formula and then do other types of computations. There's one final formula that you need to remember. Rather than dealing with the concept of resistivity, you can also take its inverse, which is called conductivity. And conductivity is symbolized by the letter sigma, which is 1 over rho. And this is a definition of conductivity in terms of the resistivity. So resistivity gives us our resistance. Our conductivity, when that's high, it allows us to conduct, which means this number is very, very small. It would make this one very, very large. So you need to remember the formula for resistivity and how it has to do with the geometry of a substance, how that resistivity is related to temperature, and in particular, this factor alpha, which is the temperature dependence of resistivity, which has to be given to you, and the concept of conductivity, which we often use in electrical theory. Maybe I'll work one problem having to do with that. You notice that if we went back and looked at our copper, which has 2e to the minus 8 for resistivity, if we took its reciprocal, this would give us 0.5 e to the 8, or more properly, that would be 5 e to the 7th, and this would give us our conductivity. So you can see the conductivity is very, very high, whereas it'd be very low for these other substances.